Okay, I think we'll go ahead and get started here. Good morning and good afternoon, everyone. My name is Michael Schwartz, and I'm the Program Director here at Fluxion. Just want to welcome everyone to our webinar entitled Take a Tour of the IsoFlux System. So there's a bunch of people still joining here, but I just want to point out a few of the WebEx features in case you're not familiar with the format. There are some buttons on the lower left corner of your screen that will toggle between full screen and a view that has the control panels. You can use the control panels for questions and answers. Hopefully everyone can hear the audio okay. You can either get that through your computer speakers or through a dial-in connection. If you're calling from outside the country, just let me know if you need a global call-in number. So at any point during the presentation, please feel free to ask a question using the Q&A panel, which is typically on the right side in the control panel screen. All of your questions go directly to me, not the entire audience. So feel free to indicate if you'd like to keep your question private, and I'll do so. Otherwise, I'm going to try to answer as many of the questions as possible after the presentation. And if I miss anything, I'll be happy to go back after the presentation and answer those directly to you. So let's go ahead and get started here. So today's webinar is divided into two parts. I'm going to first provide an overview about our recently launched IsoFlux system for doing CTC analysis. And this will cover the approach used and the principles of operation. And then towards the end, I'm going to move into some of the key downstream applications enabled by the IsoFlux platform. So just before I get started, I want to give a little bit of background about our company in case you're not familiar with us. We were started back in 2006 out of some research that came from University of California, Berkeley. And since then, we've introduced three main product families that are used in all areas of clinical research, life science research, and drug discovery and development. We have an extensive track record. We support over 300 instruments in the field all across the world. And every instrument that we place is backed by our technical support team. Here in North America, we sell all of our products direct, and then we also have a network of distributors that provide local sales and support throughout Europe and Asia. So feel free to go to our website if you're not from the US or Canada and identify your local distributor. So I want to introduce our IsoFlux system, which is our newest platform that we launched last November. And this was really the result of over 3 years of R&D to address the critical need to isolate CTCs and other rare cell types from biological samples. And when we got going with this effort, it was already quite clear that these cells were needed for downstream analysis and not just counting. So we built the system from the ground up with this goal in mind. And we also appreciated that for a CTC system to become a true standard, it had to be simple and easy to operate. And it has to be placed in any lab across the world. So this is the kind of system that we set out to build. The main limitations historically on CTC equipment has really been the ability to simply get enough CTCs to do a meaningful downstream analysis. And we know that there's very few of these cells to begin with in the circulation. And we know that clinically we can only take so much blood at any one time. So the sensitivity of the platform is critical to make sure that we can get enough cells for analysis. And this is an area that we think that the IsoFlux system truly excels at. Once the cells are actually captured, the transfer between the isolation device and the downstream analysis is a very critical step. And we optimized our platform to pass on the captured CTCs with very high efficiency using a novel collection mechanism. And as I'm sure most of you know, the transfer steps can be a critical source of sample loss and additional processing time. So we've tried to minimize this to the least amount of processing possible. And as I mentioned before, the IsoFlux system was designed to be placed in any researcher reference lab and be operated by users of any skill level. And this just makes it easier to control assay variants across multiple sites and multiple studies. So I'm sure that everyone's familiar with the main approaches used for isolation of CTCs and can appreciate that there's advantages and disadvantages with each of these methods. But I just wanted to explain our rationale for the design of the IsoFlux system. So of all the approaches out there, we initially felt that immunomagnetic enrichment offered the best combination of selectivity and recoverability. With size-based separation, we felt this was just too limiting of a selection criteria, and as well, it was difficult to get the cells, to retrieve the cells post-collection. And these other approaches, which include affinity panning and scanning cytometry, also face similar limitations with either enrichment or recovery. Immunomagnetic enrichment, and whether you're referring to a platform like the cell search system or traditional magnetic bead isolation, typically has limitations on sensitivity or efficiency of rare cell isolation. But this is where we felt that we could employ Fluxion's microfluidic technology, which has already been successfully used across hundreds of instruments. The IsoFlux system utilizes a flow focusing technology to enhance the sensitivity and isolation efficiency for rare cells. So like traditional magnetic bead isolation, the magnetic particles are functionalized with antibodies towards cell surface markers. But instead of using a large magnet across a static sample in a large tube or cartridge like the cell search system, the IsoFlux system routes the sample through a micron scale flow channel. The sample flows across what we call the isolation zone that you see here, which is really an expanded cavity that comes in contact with an external magnet that's part of the instrument. And you see that sitting on top of the channel in the schematic. The cells containing magnetic particles, the target cells, are retained on the roof of the isolation zone, while the unbound blood cells are biased from the flow forces and the gravitational forces to keep flowing towards the waste well downstream. And the flow profile through these micron scale channels is laminar and extremely uniform. So all of the cells see a very uniform magnetic field. And this is what really increases the capture efficiency. So we currently have 2 enrichment kits that are available. Each of these kits comes with the microfluidic cartridges and the magnetic beads and all the other reagents necessary for cell isolation. The CTC enrichment kit, the first product listed here, has magnetic beads that are pre-functionalized with an anti-EpCAM antibody to recover tumor cells of epithelial origin. The rare cell enrichment kit comes with the same kind of bead, but it's functionalized with a pan-mouse IgG. And this can bind your own mouse antibodies for doing customized cell isolation. So here you can define your own capture criteria using antibodies for markers found on EMT cells, tumor type specific cells, or stem cells. And these can be used as single markers or as cocktails of markers, and thus can also be used with or without EpCAM at the same time. And this kit comes with a complete protocol and everything you need to use your own capture criteria, except of course for the capture antibody itself. And these are typically either part of your own proprietary research, or as we all know, there's plenty of commercially available antibodies that might be appropriate for this kind of application. I think most people are familiar with the use of EpCAM as an epithelial marker for CTC isolation. EpCAM is a pretty logical choice for many of the common cancer types, but it's come under scrutiny recently for 2 main reasons. One is the limited CTC recovery seen on the cell search system, particularly in cancers thought to have lower EpCAM expression, such as lung cancer. The other reason is that research has shown that there can be variable EpCAM expression throughout the tumor, and then this can also diminish over time as the cells enter the circulation. This data here from Liz Panusa's group at Genentech shows that the EpCAM expression can vary up to 10 times across different tumors. This is the plot on the left. And then also within different subtypes of breast cancer shown here on the right. But one of the main points we try to make with the IsoFlux system is that the platform itself has a large influence on how a particular capture antibody performs. And using a microfluidic separation technology can greatly increase the CTC capture using an antibody like EpCAM. But it still allows other capture antibodies to be used in addition to or instead of EpCAM. So one way to show this difference in sensitivity is by using spiked cancer lines that have varying EpCAM expression. And we can surely all appreciate that cell lines are not an exact model for clinical samples, but they can certainly be useful in analytical comparisons. On the bottom here, we show relative expression data for 5 different cell lines going from low to high EpCAM expression. And then on top, we have a compilation here of CTC recovery data for some of these cell lines from the literature. And where available, we included the same cell lines tested on the IsoFlux system. So for a high EpCAM cell line like SKBR3, both the cell search and the IsoFlux system have CTC recovery in the 80 to 85% range, which is pretty good for both platforms. But when you start to dip down to a low EpCAM line, like the MDA and B231s, the difference starts to become more extreme. You see that there is over 5 times more recovery on the IsoFlux system, 64%, compared to 12% on the cell search platform. And the line right above that for the PC3s, this was an interesting data point because here we controlled for all of the extraneous variables, like we used the same staining method, we used the same microscope and the same person analyzing it, and this was done in conjunction with Prometheus, which is a diagnostic company down in San Diego. So even when using completely matched protocols on a mid-EpCAM expressing line, the IsoFlux system recovered about 2 times as many CTCs. So while we can use cell lines for analytical comparisons, clearly there's no substitute for actually doing clinical testing. And here we show a matched clinical study done at Memorial Sloan Kettering using prostate cancer clinical samples. And here we collected 2 tubes of blood from 22 patients and processed all of them the next day on either the IsoFlux system or the cell search system using standard protocols for both platforms. And if we look down at the data below, we see that 95% of these samples had more than 5 CTCs on IsoFlux compared to 36% for cell search. And you'll see throughout this presentation, we tend to think of 5 CTCs as being a meaningful number, not so much for the prognostic indication like you might be familiar with on the cell search platform, but we've qualified several downstream assays that have 5 as sort of the lower limit of detection for the assay. So we think that if we can get 5 CTCs, we can perform a meaningful downstream assay on them. Prostate cancer is generally thought of as having relatively high EpCAM expression, but the difference in sensitivity between platforms is even more profound when you look at other tumor types. So up top here, we show a collection of studies from the literature using cell search. And what you see is that the percent of samples that are greater than 5 CTCs ranges anywhere from 0 to 40% for all the indications other than prostate cancer. On the bottom, we show groups of samples that were taken from Fluxion's customers and collaborators using the IsoFlux system. And these samples range anywhere from 70 to 100% of patients having greater than 5 CTCs. 2 points of interest here. One is that the lung cancer and the colorectal cancer groups contained a significant percentage of early stage patients, non-metastatic, which we think is an important and emerging application for CTCs. And then I'll just note that the pancreatic test group here was performed on leukapheresis samples that came from biopharmaceuticals. All the other samples were done on whole blood samples. Another approach to CTC isolation that I mentioned before was size-based separation, typically using filters. And while the simplicity of these devices is attractive, studies have shown that size is not necessarily a reliable discriminator for CTCs. In the graph here, we show data from Firas that shows one of the commercially available filter devices, and it has significantly lower CTC recovery for breast cancer as compared with prostate and lung. But comparatively, the IsoFlux platform shows over 70% of patients having more than 5 CTCs across all 3 of these indications. The filters also have some limitations in terms of how much blood can be processed at any one time per device. The published numbers that we've seen are typically between 1 and 3 mils of blood per filter. So to process a complete blood tube, it can take multiple devices, which of course drives up the time and cost associated with doing a full sample. The data shown here in this particular study has been normalized to a full tube of blood, so not all of the blood was actually processed from a full tube. And additionally, once the cells are collected on the filter, there's a real risk in losing CTCs in the transfer step between the filter and recovery for molecular work. And several papers have mentioned this transfer loss. So one possible explanation for this is that CTCs and white blood cells might have a larger overlap in size than people think. The plot on the plot on the left here from Mehmet Toner's group shows the measured diameters from CTCs in a breast cancer patient. And you can see that about 30 to 40% of the CTCs would fall below the threshold of most filter systems. Most of the filters have a pore size of around 8 microns, which effectively means you need a cell 10 microns or greater to really be caught by the filter and not squeeze through. But conversely, you'll see about the same percentage of blood cells falling above the size threshold, which explains why there might be considerable amounts of white blood cell contamination and clogging on these platforms. Now, the data on the right shows a similar study from Peter Kuhn's lab down at Scripps that measured CTC cell diameters in prostate cancer patients. And what they showed was that the clinical samples, or the prostate cancer CTCs, are about 3 times smaller than the Ellen-Cap cell line, which is a prostate line that's often used in model studies. But more importantly, if you look across all 13 patients they characterized, a significant number of these CTCs would fall below the size threshold of a typical filter. So this is just some background that clarifies why we chose not to use size as a discriminator and why we prefer immunomagnetic enrichment. So with that background in mind, I'm going to shift back to the IsoFlux workflow. There's 3 main parts to the IsoFlux process. There's sample prep, running of the sample, and then transfer to the downstream analysis. To prepare the sample, in most cases, it's going to be a tube of blood drawn in a 10 cc EDTA tube, and then processed either the same or next day. And if it needs to be shipped, that's just done at room temperature in a controlled styrofoam cooler. We first start by running the blood across a Ficol gradient using density centrifugation. And then we add the magnetic beads from our enrichment kit, and they're allowed to incubate for about an hour of hands-off time. And at that point, the sample is ready to go. It's been effectively reduced from a 10 cc tube of blood down to about a 1 mil sample of effectively buffy coat with the magnetic beads added to it. And this sample is transferred directly with a pipette into our microfluidic cartridge. So it takes about 5 minutes to transfer, and then the cartridges are loaded into the tray of the instrument, and they reside in the instrument for about 40 minutes of processing time that's fully automated and hands-off. And after that, the cartridges come back out, and you can retrieve the cells off of the cartridge, and they're immediately ready for the downstream analysis. The instrument itself can run up to 4 samples in parallel, which, using the workflow that I just described, means you can do about 16 samples per day. Everything is operated from a simple touch screen on the front panel. Here you can see a sample screen where the user is running 3 of the available 4 slots. There's no other external hookups or computer connections besides the power cable. So this is what makes it really easy to place anywhere in the lab. There's also an integrated cooling deck that reduces non-specific binding and just controls for environmental fluctuations. So here you can see a schematic and a photo of the IsoFlux microfluidic cartridge. The sample gets loaded into the first well, the sample inlet well, and then at the same time you also load a running buffer into the second well, which we call the wash well. And the microfluidic channels run on the bottom surface of the cartridge, which leads up to the isolation zone that I showed before. And you can see that in the photo inset to the right. And then there's a protective lid on the top that covers the chip and protects the instrument from any kind of carryover or contamination. And this also eliminates the need for cleaning in between runs, another advantage of our microfluidic technology and our pneumatic pumping technology. So I'm going to switch over to a short video now that shows the sample loading process. And I hope that everyone can see these okay. I'm just going to explain what you're going to see first while the video is loading for everybody, and then we'll go ahead and play it. So what you're going to see is the user here is going to finish loading the sample into the cartridge using just a sample pipette. And they're going to place a couple of these samples in the tray to start processing. So I'll go ahead and start the video now. It looks like it's downloaded for everybody. So he's closing the lids right now, placing the 2 chips into the tray, and then just using the touch screen to start the processing. So hopefully everyone saw the video okay. If it didn't work for anyone's connection, I'm happy to send these out as movie files after the webinar. So as I alluded to at the beginning of the presentation, isolating the CTCs is really only the first part of the challenge in the CTC application. Getting the cells transferred to the downstream application can be just as challenging. With the IsoFlux system, we developed a novel method to retrieve the cells post-capture that has over 95% transfer efficiency off-chip. Additionally, the CTCs that are recovered are suspended in a droplet that's got only about 5 microliters of volume. And this means that the entire sample, by the time it's collected and recovered into a collection tube, can be as little as 10 to 20 microliters. And this is really critical for doing the downstream work because many of the molecular applications that are commonly used with CTCs have limited volumetric inputs. So this makes the samples ideally suited for things like gene expression, mutational profiling, next-gen sequencing, and related molecular applications, as well as imaging applications like immunohistochemistry, immunofluorescence, and FISH. This schematic is going to give you a closer look at the retrieval mechanism, which we call the cell spot. The roof of the isolation zone that I mentioned before is actually a removable cap that is plugged into the cartridge during processing. So once the run is complete, this cap is removed inside the instrument with a magnet in place to retain the CTCs. And the cap can either be placed on the included microfuge tube or collection tube, or it can be presented in a special low-volume recovery holder to minimize the collection volume. So we'll take a closer look at that method now. The cell spot cap is actually inserted by the instrument into a plastic holder that we call the low volume recovery holder, and that's what you're seeing in the photo below. The cap is actually plugged in from the underside of that white plastic cap, or white plastic recovery holder. So after the processing, the holder is simply placed on the bench, and the user can recover the CTCs with a pipette. And typically the pipette is just loaded with a minimal amount of media, so about 10, 20 microliters. And that's enough to transfer the entire sample off of the low volume recovery holder and immediately into a collection tube for molecular work. Now, alternatively, at this point, the samples can very easily be banked in a freezer for processing at a later date. And that's typically how we handle our samples internally, because it's not always convenient to, take each sample one at a time into a PCR reaction or sequencing. So we typically bank our samples for, many months at a time before we go back and process them. And that's a very stable and reliable process. So I have one more short video here that's going to show that recovery process off of the low volume recovery holder. So here the user is going to take the 4 low volume recovery holders off of the chip after they come out of the instrument and place them on the bench. And then you'll see him transfer one of the samples directly off of the low volume recovery holder and into a collection tube. So here you see the 4 cartridges being ejected after the processing run. He's going to just pull off the recovery holders and invert them. And basically, the sample is presented in a little micro reservoir or well, and you can just pipette directly off of them. So hopefully that gives a good overview about how the system operates and how it's optimized for the types of downstream analyses that are most utilized on CTC samples. So I now want to spend just a few minutes highlighting some of these specific downstream methods that can be used with IsoFlux. One of our initial adopters was Bayer Pharmaceuticals in Berlin. And their biomarker team there is interested in using CTCs in all aspects of clinical decision-making, but particularly in cases where the tissue might not always be readily available. So our initial work with them focused on simply comparing many different CTC isolation platforms. And this poster here was presented at the Athens CTC meeting last year, and it shows the IsoFlux system having superior recovery as compared to CellSearch and ApoCell and other CTC collection devices. So if anyone wants a copy of that poster, please let me know and I can pass one on. But the main goal of their effort was really to start using CTCs for molecular profiling. And FluxNet has developed a complete workflow for doing, in this case here, we're doing mutational profiling assays using a standard qPCR instrument. And if anyone wants to learn more specifically about our mutational profiling assays, we did just do a webinar last month on that specific topic, and you can go to our website to go back and catch that if you missed it. So in this data set here, we took 26 cancer patient samples from a number of different pathologies, including pancreatic, breast, and colorectal cancer. And they were processed for both CTC recovery and mutational profiling on the IsoFlux platform. So one of these tubes was enumerated, and this provides the values on the y-axis. So each of those patients has their actual CTC count. And then the other tube was used to process for KRAS mutations. So here we show that about 85% of the samples had more than 5 CTCs, which, as a reminder, again, was the lower limit of detection for our mutation assay. Then about 20% of these samples had either a KRAS or a BRAF mutation detected. So, ultimately this kind of work is going to transition into their clinical trials where they can, prospectively profile their patients and decide which patients are eligible for their targeted therapies that are coming through the pipeline. And this is another mutational profiling study that we have ongoing with Indiana University at their Horizon Oncology Clinic. So here we're testing only colorectal cancer patients that have had a prior KRAS mutation test on their primary tissue. And these patients are at all different stages, including non-metastatic. So again, we see that about 87% of the patients tested so far have more than 5 CTCs, which is above the limit of detection for the mutation assay. And 47% of these patients had a KRAS mutation detected in their CTC sample, which is more or less in line with literature values reported for the primary tissue. But interestingly, about 40% of these samples had some level of discordance from the primary tissue. And in all of these cases, it was typically a wild-type patient from the tissue was seen to have a mutation in the CTCs. And it's worth noting that in most of these cases, the primary tissue was collected at the initial diagnosis, which was on average months or years before the blood was drawn for the CTC test. So this simply highlights how the CTC profiles may change over time from the initial biopsy and highlights the main goal for CTCs in general is to have some kind of longitudinal monitoring of patients over time. Another application area that we're looking at is next-gen sequencing, and this is a great application for IsoFlux samples. One of the partners we're working with here in this area is Asuragen, which, if you're not familiar with them, is a leading cancer diagnostic and reference lab here in the U.S. They've developed some targeted sequencing panels that look at hotspot mutations of relevance to cancer. One of the panels that we've used is their SuraSeq 200 panel, and this looks at 211 unique mutations across the RAS pathway, covering genes like KRAS, BRAF, HRAS, and NRAS. In our initial analytical studies, we've shown that the IsoFlux samples can be recovered, frozen, and shipped to their core lab for sequencing. And in this data here, we spiked a low EpCAM expressing cell line, which are MDA and B231s. We did this in varying concentrations into tubes of whole blood. The cell line has a heterozygous G13D mutation on KRAS. And so from the recovery that we enumerated in a separate parallel sample, we can calculate the predicted mutational percentage based on the recovery and the expression of the mutation in that cell line. And what we showed was that the measured values on Asuragen's targeted sequencing assay correlate very well and is linear with predicted values. And this particular test was run on the Illumina MySeq sequencer. So we spent a lot of time talking about next-gen sequencing and qPCR, and these technologies get a lot of attention right now in molecular diagnostics, but much of the diagnostic workload in this country and across the world is still run using imaging techniques like immunohistochemistry, immunofluorescence, and FISH. So one of the nice things about IsoFlux samples is that they can easily be dispensed onto standard microscopy slides for any of these types of analyses. The samples have the advantage, again, of being very low volume, so they can be spotted onto a slide without having to use a cytospin technique or any kind of complicated transfer mechanism. They simply can be dotted onto a slide, and it also takes up less area on the slide, and so that reduces both the processing time, the image analysis time, and the reagents needed to run these assays. So here we're showing a thumbnail gallery of CTCs recovered on the IsoFlux system. These were imaged using automated routines on the BioView system, which is a leading analysis platform for imaging-based diagnostics. So I think this is a good spot to conclude, and I want to open up the presentation to questions. Hopefully this has provided you with a good overview of how the IsoFlux system operates and the kind of performance that you can expect using the platform. So please feel free to ask any questions using the Q&A panel. I'm just going to take a minute here to review the questions, and then we'll start answering them. If you'd like any additional information, please use the email contacts below. Sales@fluxionbio.com is good for product quotations and sales inquiries. And then support@fluxionbio.com is useful for any kind of product or technical questions. Okay, there's a question here. Are the CTCs recovered in buffer? And is there any option to recover the cells in the patient's blood plasma? Which is a great question. We supply a buffer with all of our kits, and that can typically be used to recover the CTCs at the end. But there's absolutely a workflow where you can recover the cells in the patient's blood plasma. You can simply preload the collection tube with the plasma, and then that'll be automatically collected when you recover the collection tube. Or if you're using the low volume recovery holder, you can load your pipette with the patient's blood plasma, 10 to 20 or more microliters of that. And then as you aspirate the cells off of that recovery holder, you'll be suspending the cells in the plasma, and that can be transferred to a downstream collection tube. Okay, there's a question about the purity of CTCs collected from the eluted volume. The purity of the sample is generally between about 2 and 20%, which in absolute terms means that a typical CTC sample will have anywhere from 5 to 100 CTCs, and the total amount of cells, which includes any kind of white blood cell carryover, is going to be about 500 to 2,000. So purity is a metric that's not often tracked. We routinely measure purity on every sample because we feel it's important to know what the purity of the sample is before moving to the downstream assay. And we've characterized several different assays, including some that I've mentioned here, mutational profiling, sequencing, gene expression, are all very adequate and work just fine at that level of purity. When you look at purity across other platforms, it's a little challenging because there are not many published studies that report that data, primarily because it's difficult to detect, and the references that we've seen have shown that purity on filters is well below 1%, meaning that there's still anywhere from like 20 to 50,000 contaminating white blood cells. So we feel like this is going to be the highest quality of enrichment so far of a commercially available device. Okay, there's a question here: are the cells viable after purification, and do you think that they could be used to look at cellular responses? So yes, we have done tests to confirm that the cells are viable after collection. We can do this through staining methods, and we've done some work in vitro to culture the cells after collection. So the instrument itself has a very gentle processing on the cells. The flow is controlled in our microfluidic channels in such a way that the shear stress acting on the cells is very minimal, and certainly no more than it sees in the vasculature. So the cells are viable and should be available for any kind of downstream in vitro culturing or functional assays, as I think this question is referring to. Okay, there's a question here about how to add your own antibody and what that protocol is like. So this is using our rare cell enrichment kit. And the the preferred method here, we have a complete protocol that we supply with the kit, and this is available online. If you want to go ahead and take a preview, you can look in our download section and actually get the complete protocol. But the simplest and most effective method is what we call the direct method. And this involves taking your antibody and direct coupling that to our IgG bead. And this has the advantage of better sensitivity, but also allows you logistically to prepare your beads ahead of time in a larger batch, which will just keep more consistency as you run any number of samples from that batch. Okay, there's a question here. How does the IsoFlux system compare to the DEP array? It's a good question. If you're not familiar with the DEP array, this is a platform that uses dielectrophoresis to effectively manipulate single cells out of a sample and move it to kind of a downstream single cell approach. The main difference is that the DEP array doesn't do any enrichment up front, and it's got a very limited sample input. I hope I don't misquote the specifications, but it's something like you can only add about 14 microliters of volume and some thousands of cells, but not hundreds of thousands or millions of cells. So in order to use the DEP array, you have to have some kind of enrichment up front of it. And so the IsoFlux system is designed to do that enrichment, so we can actually process the sample right from the beginning, which is typically a blood tube. And we deliver the sample in a highly enriched and highly concentrated format. And once you have it at that point, there's any number of ways that you can analyze it. And if you're interested in doing single cell work, we have a protocol that allows you to, manually pick single cells. There's automated instruments that will help make that process a little bit easier. Or you can consider using the DEP array downstream. But, it's very important to have a high quality enrichment up front of that process. Okay, there's a question here. Why is your system better than cell search? And is this due to better capture by our kits or a stronger magnetic field by the microfluidic system? Definitely a good question. I tried to touch upon that a little bit in this presentation, but just to clarify, it's not necessarily a stronger magnetic field within our platform. It has more to do with the uniformity of the magnetic field and making sure that every cell that has a magnetic bead is properly exposed to that magnetic field to improve the capture. But there's other kind of nuances here that have a rationale in physics to explain why it increases the capture efficiency. One is the magnetic moment created by the beads that are attached onto the cell. One key difference that I didn't mention is that we use the larger magnetic beads that are about 4 microns in diameter, whereas cell search uses a ferrofluid which has nanometer scale particles. What that means is that we've characterized our system that if you have just one bead attached to the cell, we can capture it on our platform. When you use the ferrofluid, you typically need a coating of the particles to get enough magnetic moment to be captured on a magnet. And what that translates to biologically is that we can capture cells that have lower antigen expression. So as I mentioned, if you have low EpCAM expression, all you need is one bead to couple to the cell, and we have a good chance of capturing it. So that's one of the key differences. And I guess the other is kind of the fact that our system is a flow-through system. So it's not perfectly analogous to a fax instrument, but you can think of it like that, where the cells are flown in an orderly fashion across, in the case of fax, it would be a detector. In the case of our system, it's an isolation zone where we capture the cells as they flow through the channel. But that flow-through process is key to make sure that every cell has a chance to be captured, and it also minimizes the contaminating cells that are, end up in the final sample. Okay, well, I think we're just about out of time. I appreciate all the questions, and if there's any that I missed, I'm more than happy to follow up individually after the presentation. And there will be a recording of this webinar available in the next couple of days. It'll be posted to our website, and we will email the link out to everybody. So feel free to look for that if you want to share with your colleagues or go back and look at this again. So again, thanks to everyone for participating today, and we'll look forward to following up with people individually if you have any additional questions. So thanks.